Chapter 9.2, Analyzing Rational Functions. A rational function can have a vertical asymptote at the NPV where the graph is undefined, or, we haven't seen this yet, but it could have a point of discontinuity where the graph does not exist. A point of discontinuity is represented by a hole in the graph, so a point, or an ordered pair, which is an open circle, appears on the graph where it is not continuous. We always have to factor both the numerator and the denominator. When factored and simplified, the numerator indicates the x-intercepts. If you are able to reduce, so divide out a factor from both the numerator and the denominator, then the NPV for that factor represents a point of discontinuity. When factored and simplified, any remaining NPVs represent a vertical asymptote. Sketch the graph of the function f of x equals x squared plus 2x minus 3 divided by x minus 1. So let's state our NPVs. The bottom is already factored. X minus 1 can't equal 0. When does x minus 1 equal to 0? When x is equal to 1. So the NPVs would be x equals 1, or you could write x cannot equal to 1. Whichever way you write it, I don't care. Factor and simplify. So our numerator, x squared plus 2x minus 3, two numbers that multiply to negative 3 and add to 2 would be 3 and negative 1. So it factors to x minus 1 and x plus 3. Our function becomes f of x equals x minus 1 times x plus 3 over x minus 1. Then we can divide out x minus 1. So we're left with our simplified version, f of x equals x plus 3. As we said up here, if you're able to reduce, divide out a factor from both the numerator and the denominator, the NPV for that factor represents a point of discontinuity. So we were able to divide out x minus 1 from the top and bottom, which means the NPV for this factor, x minus 1, which is 1, our NPV of 1, represents a point of discontinuity. So x cannot equal to 1. So there is a point of discontinuity at x equals to 1. Find the y value of this point. To do that, we're going to take the simplified function and we're going to plug in the x value of the point of discontinuity. So we're going to do f of 1, which is 1 plus 3. So f of 1 equals 4. So the y value is 4. Therefore, our point of discontinuity is at x equals to 1, y equals 4 is the point of discontinuity. So to draw a graph, it simplifies to the linear function x plus 3, a y-intercept at 3, and a slope of positive 1, so up 1, right 1, and then down 1, left 1, Our point of discontinuity is at x equals to 1, y equals to 4. So I'm going to put a circle there before I draw my line. I have a line on this side and then on this side. There is our graph of our rational. We have a point of discontinuity represented with a hole. And we notice that we don't have any asymptotes in this one because our only non-permissible value was factored out. So it became a point of discontinuity rather than a asymptote. Analyze the behavior near the non-permissible value, which is at x equals to 1. As x approaches 1 from the left or the right, y approaches to 4. Okay, so here x approaches 1 but never equals 1. And here y approaches 4 but never equals 4. Compare f of x equals x squared minus 3x divided by 2x plus 6 and g of x equals x squared plus 3x divided by 2x plus 6. So our NPVs, first of all, if we take 2x plus 6 equal to 0 and solve for x, subtract 6, we get 2x equals negative 6, divide by 2, we get x equals negative 3. So that's our NPV for this one. And over here, same thing, 2x plus 6 on the bottom. So x equals negative 3 is our NPV. Factor and simplify. Factoring f of x, we get x times x minus 3. We factor out the common factor of x on the top, and on the bottom we get 2x plus 3, factoring out the common factor of 2 from the bottom. Over here for g of x, we factor out the x on the top, we get x times x plus 3, and on the bottom, factor out the 2, we get 2 times x plus 3. Then we can divide out those two x plus 3's, so g of x becomes x divided by 2, which we can also write as 1/2 x. So on the previous page it said when we factor the top, when factored and simplified, the numerator indicates x-intercepts. Going back, we have the numerator x and then x minus 3. So the x-intercepts would be 0 and 3. X equals 0 when x equals 0, and x minus 3 equals 0 when x equals to 3. Then, when factored and simplified, any remaining NPVs represent vertical asymptote. We have a remaining NPV here of x equals to negative 3, so our vertical asymptote is x equals negative 3. x equals to negative 3. Then we can plot our x-intercepts, which were at 0 and also at 3. Let's use our calculator to find some more values here. Let's say that I pick a value between our two x-intercepts. I'll pick 1, bracket 1 squared minus 3 times 1, close bracket, divided by bracket 2 times 1 plus 6, close bracket, enter, and we get negative 0.25, so just below there, just below the x-axis. Let's try the same for 2, so I'm going to go back up, hit enter, so I can just change my x values that were 1 to 2s. So delete that and put a 2. Delete the first one, put a 2, and delete that one and put a 2. And we get negative 0.2, so a little bit closer. Let's try when x equals to negative 2. So bracket negative 2, close bracket, squared, minus 3 times negative 2, divided by 2 times negative 2 plus 6 gives us 5. So at x equals negative 2, y equals to 5. And then let's try x equals to 5. Five squared minus 3 times 5 divided by 2 times 5 plus 6 gives us 0.625, so a little bit above the, so about there. Okay, so this is definitely going to make this shape here. Something like that. And then there's going to be another part on the left side of this vertical asymptote. So let's plug in some values there. Let's see when x equals negative 4. Negative 4 squared minus 3 times negative 4 divided by 2 times negative 4 plus 6 is negative 14. So negative 4 and negative 14. We will try negative 5. Negative 5 squared minus 3 times negative 5 divided by 2 times negative 5 plus 6 gives us negative 10. X is negative 5, y is negative 10. Let's try negative 6. Negative 6 squared minus 3 times negative 6 divided by 2 times negative 6 plus 6 gives us negative 9. Let's try negative 7. Oops. Negative 7 minus 3 times negative 7 divided by 2 times negative 7 plus 6 is negative 8.75. And let's try negative 8. negative 8 squared minus 3 times negative 8 divided by 2 times negative 8 plus 6 gives us negative 8.8. So it gets higher, and then it starts to go down again. So that's going to look something like this. Graphing g of x, it simplifies down to a linear function, which is 1/2 x, so a y-intercept at 0 and a slope of 1/2, which is rise 1 and then run 2. So up 1 over 2, up 1 over 2, up 1 over 2, down 1, left 2, down 1, left 2, down 1, left 2, down 1, left 2. Then we want to look at our NPV. We see that the factor that had that NPV divided out, and if we look over here, if you are able to reduce, cancel, divide out a factor from both the numerator and denominator, the NPV for that factor represents a point of discontinuity. So we have a point of discontinuity at x is equal to negative 3. We need to know the y value of that point to be super accurate. So before we graph it, down here it says coordinates of the point of discontinuity on the second graph. Let's figure that out. We know that x equals negative 3. We take that point and we plug it into the simplified version of g of x. So g of negative 3 equals 1/2 times negative 3. G of negative 3 equals negative 3 over 2, or negative 1.5. So at the point x equals 3 and y equals negative 1.5, we have an open circle to represent our point of discontinuity, and then we can join the rest of the points together. There we go. So that's our point of discontinuity at negative 3, negative 1.5. Match the equation of each rational function with the most appropriate graph. Explain your reasoning. We need to factor so that we can see if we have a point of discontinuity or a vertical asymptote. This one, x squared plus 2 doesn't factor, so x squared plus 2 over x squared minus x minus 2 factors to x minus 2x plus 1. We can't divide out either of these two factors, so we have NPVs are x equals negative 1 and x equals 2, because if x is negative 1, then x plus 1 equals 0, and if x is 2, then x minus 2 equals 0. Either one of those situations would make the denominator 0. So those two are NPVs, and because neither of these factors can be divided out, that means that both of these NPVs are vertical asymptotes. Okay, so we have two vertical asymptotes, one at negative 1, one at positive 2, which is the situation that we see in graph 3. We have a vertical asymptote at x equals negative 1 and also at x equals to 2. So graph number 3 is a of x. B of x equals x minus 1 over x squared minus 1 is a difference of squares. It factors to x minus 1 x plus 1. Then we have our NPVs would be when x is -1 and also 1. We can divide out x minus 1. The factor you can divide out, the NPV for that factor is the point of discontinuity, so that would be x equals to 1. So x equals to 1 is a point of discontinuity. And then x equals to -1, that factor is still there. We still have x plus 1 on the bottom of our rational, so that would be a vertical asymptote. X equals -1 is a vertical asymptote. And then b of x simplifies down to 1 over x plus 1. Looking at our graphs, we want to find the graph that has a vertical asymptote at x equals to -1 and a point of discontinuity at x equals to 1. So graph number 1 has a vertical asymptote at x equals to -1, and it has a hole or point of discontinuity at x equals to 1. X equals -1, and here x equals to 1. So that is our graph for the function b of x. That means that graph number 2 has to be for c of x. So let's see how we can show that. Let's factor c of x equals x squared minus 5x plus 6. Two numbers that multiply to 6 and add to -5. They would have to both be negative because they multiply to a positive but add to a negative. Two numbers that multiply to 6 would be -2, -3, that also add to -5. X minus 2, x minus 3, and then divided by 3 minus x. Now I can change the order of the bottom. C of x equals x minus 2, x minus 3. I can write my x first, so it's -x plus 3. And then I can factor out a negative from there. C of x equals x minus 2, x minus 3 divided by negative bracket x minus 3. Then I see that my NPV is when x minus 3 equals 0, which would be when x equals to 3. And I also see that I can divide out x minus 3. So if you can divide out that factor, then the NPV for that factor becomes a whole. So x equals to 3 is a point of discontinuity. And there are no vertical asymptotes since our only NPV divided out to become a point of discontinuity. So c of x simplifies to a linear equation, which is x minus 2 divided by -1, or we can write that as c of x equals negative bracket x minus 2. You could also multiply the negative into the brackets. So now we've shown that graph 2 is definitely c of x, and we can see our point of discontinuity at x equals 3. That brings us to the end of Chapter 9, Lesson 2.